Bismillahirrahmanirrahim. Good evening, everyone. Today, our lecture will focus on two kinds of diode. Actually, I explained all this information at the previous lectures when I was talking about the Zener diode and Schottky diode. After that, we will go to do something like comparison between these two different diodes with the lead diode, why the lead emit light, why the diode be like resistance in some situation, in another situation will be like short circuit. We will focus on all this information, but at first let me do simple review. Let me focus on the PN junction. Why? Because this will be the first setup to us to can go to understand all the important information related with diode, related with. Let me go to another slide. Let's talk about what is the PN junction, how it formed. Like we know, PN junction is two sides doped by using different elements. We can say we must note that these two sides made from silicon, and one of them doped with phosphorus. That's mean five electrons of the last shell. The p-type or side doped by using a boron element belong to 3 electrons family. How it formed? Let's focus on all of these. Let's try to answer this question. A PN junction is a boundary between two different extrinsic semiconductor material types. Like I say, the two types made from the same silicon material, namely p-type and n-type inside a semiconductor. Now, let's focus on this image. I make this image to can illustrate what happened inside N and p-type. Here, n-type, that means majority are electrons with few minority holes, and the minority holes here, the positively charged. Here we used phosphorus, has 5 electrons at the last shell. P-type, majority holes, minority electrons, and these elements are boron, 3 electrons at the last shell. Now let's calculate all of them. It's just theoretically, because we do that at the lab at the same time by using vibration process. Let's say we can put plus between all of them and calculate all of them. What will happen? Actually, we will focus on these important two words, the depletion region. When we calculate all of them, the depletion region will start to create. What will happen after that and before that? Let's go to next slide to can illustrate all this important information. Here, the depletion region is started. What will happen here? The diffusion, I mean the majority, will start to travel to p-type and the same thing from p-type. After that, and when the diffusion is started, the depletion region start to create. Create to be what? To be something like wall, to avoid, to prevent more diffusion from the two types. But here we will have some questions here. Here, at first, the depletion region is created. It's done. No more diffusion, carrier charge without using any power supply. What does mean? Like we see here, we have just ions, because that's why let's say, because we physicists, or because we researchers, we must put question mark in anything. We must understand, illustrate anything in physics department, physics field. Here, Like we're seeing, we have donor ions near from n-type. On the same situation here, we have acceptor ions near from p-type. Why? Because they are by depending on the attractive force, okay? But the important phenomena, here we don't have any carrier charge. Why? This is the first question. And why we have ions in the both sides. We know donors here why, acceptor ions here why, because they're attractive. But actually, why we have ions in this place? This is the second question. The last one, or let me don't say last one. The another question is why the electric field came from n-type to p-type. Let's focus on these few questions and start to try to answer all of these at the next slide. The depletion region acts like wall to prevent the diffusion from both sides. Like I said before, let's go to another slide. What is the depletion region? The depletion region is important to us because that I said we must focus on this region because we will depend on it. We will study and note some important information when go to the diode, or actually before going to diode, when we connect or use this P injection by reverse bias, forward bias, zero bias, we will see some difference in this depletion region because that we must know actually what is the depletion region. The depletion region is a region will create when the p-n junction is created, and it's be the middle of the junction. Actually has many names, but the famous one, the commonly one, is the depletion region. But at the same time has many names like depletion layer, zone, junction region, space charge region, or space charge layer. But the most common name is depletion region. Now let's focus on the only element left in the depletion region are ionized donor and acceptor donor or impurities. Why? We can note there's no free carriers inside it, just ions. Why? Why we don't have any charge carriers in the depletion region? When the diffusion is started, the electrons and the holes will be very close together. And when all of these will be close together, this will start to destroy each other because that we don't have any carrier charge inside the depletion region. Now, let's focus on another question. Why we have ionized donors and acceptors, like I said before, in both p and side when the depletion region is created? Actually, because when the electrons will diffusion from n to p, will leave ionized donors behind. That's mean because the diffusion electron, we have donors ions near from n-type. And at the same situation, because the Hall's diffusion, we will left behind the Hall's diffusion. When the Hall's diffusion is starting, we can say, what will happen? The holes will left behind its acceptor ions. That's mean the main result, the main reason we have acceptor ions near from p-type because the Hall diffusion. Let's go to another side. Why the electric field is created from n to p? Why not from p to n? because with diffusion, the free electrons and holes around the junction will create an internal electric field. What will do, what this can make to do this change, the internal electric field? The internal electric field tries to stop the diffusion of majority carriers of each side, because that the electric field will be from N to P instead of P to N. The main reason to answer this question is the internal electric field in this region. This very clear image, because that I selected it. This is from chapter 4. I put it all the sources at the last slides. Here the depletion region is created, and P here the electric field from the side, this space charge region or depletion region, the same name. Diffusion force on electron will be from this side. Diffusion holes from P to N will be from this side. Conclusion: the p-n junction is very important, because that's sure I decided to do simple review on it before going to Zener and Schottky diode. It's very important section. Why? Because it has relation with renewable industries and relation with all diodes kind, and relation with the lead generation. That's very important industries to us. The depletion region is key to explaining the modern semiconductor electrons like diode and variable capacitance diode, like I said before. Now, I created this figure because by myself, didn't take this image from any source. Depending on this equation, we know the mobility of electrons is bigger than the mobility of holes. Actually, 103,350, it's bigger than 450, because that the N type must be bigger than P side or P region, not like this image here, the N equal P. But this, I think, theoretical, but typically, because the mobility of electrons bigger than mobility of holes, and region must be bigger than P. Now we will focus on three bias kinds. Number one, zero bias. Two, forward bias. The last one is reverse bias. Let's go directly to zero bias. What does mean zero bias? That means we didn't calculate the p-n junction with power source. Just we will calculate the two terminal of this p-n junction with the same point, and after that to the earth terminal, like that. And we will note more diffusion from the two sides. Let's go deeply to this topic. No external potential energy is applied in the p-n junction when the diode terminals are shorted together. We connected the two terminals together by using the same point, and after that take this point to earth node. A few holes, majority carriers in the P material with enough energy will move across the junction against the barrier potential. Here, a few holes in P type, that's mean the majority, with enough energy will move across the junction against this barrier potential. This is the forward current, IF. Let's give appropriate definition to IF. Is the forward current made because the diffusion holes in P type, or few holes diffusion from P to N with enough energy can pass from this wall, I mean the depletion region. Let's go to reverse current, IR. or IR. Yes, IR would say. Let's give appropriate definition to reverse current. IR is the current created because the holes generated in the N-type material, minority carriers with enough energy can overcome the potential barrier in the depletion region and can cross in this junction. That means IR will focus on all were related with minority carriers from N to P. Let me take just one step back. Here, from P to N will be the holes the majority will start or will try to pass from the depletion region. But after that, at reverse current, the holes in minority will start to all try to pass with enough energy. Let's come back here. This will be better. Holes, here the majority, will start to diffusion from P to N. And the minority, what is the minority here? Is the holes will start to diffuse from N to P. This is the main purpose, the main phenomena in the zero bias. The potential barrier discourages the diffusion of any more majority carriers across the junction. The potential barrier will be the fact will be the important coefficient to us because it will discourage the diffusion of any more majority across carriers across the junction. And at the same time, we will discourage the minority carriers to drift across the junction. That's mean from P to N, from a majority P to N will be diffusion. And at the same time, the potential barrier will discourage the drift minority holes to P. Let me come back to this. That's mean this arrow, that's mean diffusion. This arrow, that's mean a drift. Then an equilibrium will establish when the majority carriers are equal and both moving in opposite direction, like that. Diffusion and the holes will do something like drift. After that, the depletion region is created. Why we say zero applied bias? Actually, because we don't have any electric power in the circuit. The net result is zero current flowing in the circuit because that we say zero applied bias. The junction is dynamic equilibrium. The minority carriers are constantly generated due to the thermal energy. So this state of equilibrium can be broken by rising what? But rising the temperature because it's dependent on temperature because like I said before, here due to thermal energy. But when broken by rising the temperature of PN junction, this phenomena what will gain from increasing the temperature. Increasing the temperature, that's mean increasing in the generation of minority carriers, something dependent on another element, and this element dependent on or by increasing it, we will do or say some increasing in the minority carriers. Let's go to another slide. Now, let's take a look about on the forward applied bias. What does that mean forward? That means we put the P region with positively terminal minus N region with negatively terminal, and the depletion region will be narrower than the ordinary p-n junction, and we will say diffusion from the both sides, pn and n to p. Here the diffusion current, the circuit will be like that. This is the diode. If this external voltage becomes greater than the value, here we have important condition. At silicon must be 0.7 and or more to can see the current can through from the diode, can through from p-n junction specifically, and 0.3 at germanium, less than silicon. The potential barrier V bar will be overcome and current will start to flow. Let me, maybe I do some mistake here. Yes, I explain. Why? Let's focus on why and try to answer this question. Here, because the N negative voltage pushes electron toward the junction, giving them the energy to cross over. That means the negative voltage here will be the main reason, the main coefficient to us, because by using it, it will give the enough energy to electrons towards the junction, giving them the energy to cross over, to come past, and combine with the holes being pushed in the opposite direction towards the junction by the positive voltage. That means we have two important coefficients. Number one, negative voltage will push the electrons to come past the barrier. Number two, the holes will discourage, will give the enough energy to holes to opposite charge to can't pass from the barrier. Now I take this column from video on YouTube. Another physicist was trying to calculate, was trying to write this diagram by his hand. Okay, here, like we said, forward applied when I do simple change in the power voltage, 0, 0.1, 0.2, 0.3 until 0.6, 0.7, all the, and we'll see increasing in current, that's right, but it's very narrow, it's very small, experimentally near from 0 until 0.7. After that, the current will exponentially increasing exponentially. Then high current flow through the diode with little increase in the external voltage. The diode here will be like a short circuit because low resistance here. We can't say low resistance, or specifically reason is narrow depletion region. Summary, this condition presents the low resistance path through the p-n junction, allowing a very large current to flow through the diode with only a small increase in the bias. The actual potential difference across the junction or diode is keep it constant by action of the depletion layer at approximately 0.3 germanium, 0.7 for silicon. Here, reverse apply, the last one, the N will be with positively terminal, P with negatively terminal. The depletion region will be bigger than forward bias, and we will dealing with diffusion from the both sides, majority of the both sides. The diode here will be like an open circuit because a huge depletion region, like I said before. Here, at like the approximately diagram, and here at forward bias, reverse bias. Sure, the diode will not allow the current to through from it because that we use it to protect our devices, to can prevent the leakage current, but this theoretically. But typically we facing some saturation current or leaking current near from zero. The diode at reverse bar applied will be until here, and after that, if we pass the reverse breakdown voltage, the current can through from it, and actually we will lost our diode. Now let's talk about the first kind, is the Zener diode. What is the Zener diode? It's a heavily doped silicon crystal diode which allows current to flow in the forward direction in the same manner as an ideal diode. Okay, why Zener diode is very important to us, and what his great characteristic, because that it's very important to us. Now we're saying like ordinary diode. No, the situation is different. Like ordinary diode, just at forward direction, but it also permits the current to flow at the reverse direction. This the important phenomena at the Zener diode. When the voltage is above a certain value known as the VZ, breakdown voltage, V source bigger than VZ, the current can through. Something has difference from the other diodes. Why the Zener diode can be like that? Why can let the current to through from the two sides? When we apply V bigger than VZ, the depletion region will vanish, and large currents start to flow through the junction. VZ is different from VB, the ordinary diode. Here starts from 1.2 until 200 volt, depend on which current we're dealing with. Zener diodes are used for voltage regulation as a reference element in switching application, clipper circuits. What is the Zener current? And let's wondering if we have a minimum current or saturation current like the ordinary diode or not. Yes, we have minimum current or saturation current like ordinary diode, and the current IZM of Zener diode, it's a maximum current that can flow through a Zener diode. It's rated voltage. Here, like we say, like the ordinary diode, but here the results of voltage is different, but actually has the same diagram. After this point, the current will be like that, negatively and toward this side. Here, narrow depletion region. Here, at reverse biased, like we're seeing here. Why the Zener diode is always reverse biased? What happens if Zener diode is forward biased? At reverse biased, Zener diode exhibits controlled the breakdown, something like control point, control room on the breakdown voltage, allows current to keep voltage close to the Zener breakdown voltage. It behaves like a normal signal diode, passing the current increasing linearly with voltage, but as soon as reverse voltage applied across the Zener diode attains the breakdown voltage of the device, a large current starts to flow through the diode. Here, when we apply a voltage more than Zener voltage, the bottom of the sine wave gets clipped off. I mean this until this line will be like that, will be clipped off. On the top output here is a swing. This from -8 until 2.6. We will see these waves arranged between these 2 points, 0.8, 2.6. We can say after this clip off can say something like we can change the current from AC to DC by using this setup. Step. Schottky diode. Now the second type of diode is Schottky diode. Has interesting shape here like ordinary diode, but here has 3 legs and different shape, different form. Let's know why. Here Schottky diode advantage, a low forward voltage drop 0.3, 0.4. Why it is important to us? Because by using this step will prevent, will save more voltage. For example, if I use a voltage source equal 10 volts, and with diode like Schottky 0.3 starts from 0.3, that's mean I will have 10.7 volt. But if I use ordinary diode, need 0.7. That's mean I will save less than voltage, equal 9.3. This is the main idea about 0.1. This allows a Schottky diode to consume voltage less than standard diode. And the number 2 feature, fast switching ability. It's creating faster. This makes them an ideal choice for radio frequency application, any device with low voltage requirements. Fast recovery time, less noise, better performance. Performance and cost is very important in any industry. But like anything in our life, like it has advantage, it has disadvantage. The disadvantage here, reverse current is more than the ordinary diode. Why it's very important in solar cell? We use Schottky diode in solar cell more than another industries. Like I think Schottky diode can help to maximize solar cell efficiency, increase the efficiency of solar cell with their low forward voltage drop by using this feature, low forward voltage drop. Also help to protect the solar cell from reverse charge, leaking charge. Let's focus on this strange shape. Why this diode has 3 legs and different from ordinary, approximately ordinary diodes. At first, we can say this the metal part anode will be positively charged, made from metal. From what? Gold, silver, or platinum. Actually, this the good reason to make this Schottky diode, this kind, expensive than the other, sure. Second one, the Schottky barrier. It's the junction between metal and semiconductor. The last one made from semiconductor and will be made from silicon and negatively charged. Here we have some similarity just in shape with BGD. What is BGD? This bipolar junction diode. Some similarity in shape, but inside it's big difference between them. Here, metal positively and made from gold, silver, platinum, a Schottky barrier. Here, the silicon made from silicon and will be negatively charged. Here, it's a different name, different job. It has similar shape with BGD. BGD has 2 kinds, NPN, PNP. The middle will be the bias, and the 2 sides that's right, will be from the same, by using the same letter, but here it's more than majority from the right side, and the same situation here. Schottky diode is unipolar device. It's important. Let's focus on it. Another difference between them. Schottky diode is unipolar device dealing with only one charge. Carriers plays a role in transportation. Bipolar junction barrier dealing with two charges, electron and hole at the same time. Now let's focus on the lid. The great invented, the great invented, and we can say is something like revolution in light field. Like we say, has two terminals and made from p-n junction, but let's see why can emit light different from the other, or what the difference between it and the ordinary lid. Let's go deeply to the information. Let's our type of semiconductor called light emitting diode, which have achieved particle realizing through the use of high brightness blue developed in 1993 based on germanium gallium nitride. They are attracting increased attention in fourth type of light. What is the light emission in LEDs? LEDs in a privation of light emission diode and a device which emits light by flowing a current to the p-n junction like a semiconductor laser. Actually, we must note at first, some think this kind of LED, the LED field or the LED kind share the same characteristic with laser. Both of them belong to direct band gap. It emits various wavelength light, can create light to us, emit light to us in three different fields. The ultraviolet, visible, and infrared regions. Visible, we will focus on visible. All of these three fields will depend on the corresponding to energy band gap, its energy band gap. But we will focus on the visible. Because I talked about the infrared radiation and ultraviolet radiation, let's focus on this image here. The human eyes can focus on all these colors, start from 400 nanometer until 700 nanometer. After that will be infrared radiation. We can see to these high nanometers, to high wavelength, and less than 400 nanometer will be an ultraviolet radiation field. Now, what is the LED explain? LED stands for light emitting diode. Let's lighting products produce light up to 90-100%. That means high efficiency, something like near from ideal conditions. That means efficiency is very high than ordinary light bulbs. But let's focus, let's discuss why this led something like revolution in light industry. By comparing with conventional light sources, convert electrical energy into heat. This kind of light will skip go to heat, and after that, from going to heat, and after that going to can create or emit light. This kind of light will go directly to emit light, not like the ordinary light, delivering efficient light generation with little wasted electricity. And suddenly will go to emit light by skipping the heating setup. How do LEDs emit light? Actually, here we will focus on the recombination. The electrons and holes, the majority at the both sides, will do something like recombination, and in the depletion region, by that it can emit light. Let's see how. Light emitting diodes are semiconductor light sources that combine p-type semiconductor, large holes, n-type, large electrons. Here, light, by recombine between the majority from N and majority from P, and after that it can emit light. Applying a sufficient forward voltage will cause the electrons and holes to recombine at the p-n junction, releasing energy in the form of light. Let's go to another slide. Lights we see here at E equal Eg, electrons could jump to here and left behind it holes more than energy band gap, jump to this point, and after that come back to this point. After that we'll come back to, after the time life, or the narrow, the very small seconds. After that the electrons will come back to another point in the valence band. When the electrons come back to this point again, at first jump to this point and come back to this point. From this point and the conduction band to valence band, when came back, the photons will emitted. Electrons band diagram of direct gap semiconductor. Battery connected across the p-n junction makes the diode forward biased. Here we will focus on the light. Always we will use forward biased. The Zener diode, always we will connect it by using reverse biased. We must be careful by these different situations. Pushing electrons from N to P, that's mean diffusion, and diffusion holes to N-type, to N side. Electrons and holes cross the junction and start to combine. But here we have important thing we must be wondering and try to solve this question. Why here the electrons, when come back to the valence band, didn't emit heat? Why it's emitting light to us? We will say, we will find the solution at the next slides. Here, let's focus on the type of lid and take important feature from this slide. Here we have different types of lid. Ordinary lid, the COP, SMD, RGB. It's very interesting because has 4 terminals, 4 legs, and 3 terminals here. Another kind, we use it in calculator, scientific calculator, watch. If I use the same distance, I will take 9.9 and I will try to put light to create, because we researchers, we visit to can create high intensity from one of these kinds, to can put it in my shop, in my store, in my markets, to can take high efficiency with available energy, available cost. This will, it's very important to us. By using the same distance, I can put 10 lids, 40 lids of SMD, and 342 lids at the same distance, 10.10. Now, by this way, I could to generate a high intensity of LED lights, and that will depend on my purpose. I want how much efficiency I want to can put it in my office, storage, or market. Now, let's say by using this LED, we can generate many colors. That will depend on the material, but that's available. We can generate colors like we want. Now let's talk about the advantage: long life, efficiency, high brightness, exponential color range, low radiated heat, immediate illumination, directional lighting, more controllability, and smaller. High efficiency, smaller, available cost. That's mean it's safety. That's mean available. That's mean great thing. We can use it in our industries and will be available to anyone. We can do marketing to anything has these four characteristics, because that it's successful in our world. We use it, and maybe in every place, in traffic lights, and lights to say something like be careful, waiting, or the change office use this technique to say the dollar increase, the dollar decrease, the euro, something like that, by using different color, red, yellow. This important here. This plot, this diagram illustrate to us different waves, different colors. Start from IR 1.8 volt and 3.5 volt at weight color. Different from the PN junction, because at PN junction, the exponential current will start until 0.6, 0.7. It will change the play depending on material used. Like I said before, we can generate many different colors, but depending on which material we dealing with, this makes it possible to customize the color to make certain wavelength specifications required for applications that use traditional bulbs as light source, traffic, automotive lamps. This, when we dealing with different materials, we can generate different colors, something like a green with germanium phosphorus until 2.2, and this diagram illustrates to us blue, green, yellow. Conventional silicon diode don't emit light. Why? Because conventional silicon diode is created by thermal equilibrium. That's mean when the electron will come back to another point in the valence band, will emit heat instead of light. Because the recombination energy becomes thermal energy, the LED diode and the laser diode, like I said before, belong to direct band gap. Let's say all of these great application like diode and LED and many things like that dependent on the same PN junction. All that belong to this great physicist, this Russell Ohl, started in the mid of 19th century, and discovered the PN junction and photovoltaic effects in silicon on 23 February 1940, rest in peace. That leads us to development of junction transistor and solar cells. All of these because this guy. That's it. Thank you for watching. Thank you about your patience. The sources takes some information from chapter 7, the p-n junction from this source, semiconductor physics and devices, to this author, and the other one were from different links, different websites from YouTube, Google, something like that. Thank you so much. Have a good day. Let me stop recording.